Hello everyone, we're going to start 8.3. We're going to take some class notes on simplifying radical expressions, something I know that you did with Mrs. Martin last year in geometry, but we will review this, and these notes are to be taken on the 3rd of April. Our first rule says if you have two roots, so you can look at this either way, but if we look at it on this side, two roots being multiplied, as long as they have the same index, we can multiply them together and put them under one root rather than keeping them separate. Or if you have one that is one root, under one root, you can break it up and write it as two separate. And the quotient rule works the same way. Two roots being divided with the same index, you can put them underneath one root. If you have one entire big root, the first thing I usually look for is the bottom perfect? Then I want to break it up and write it this way. So a lot of times I'm using this side and writing it like this if the bottom's perfect. If it's not perfect, I'm working to see if I could reduce that fraction. Majority of times here, I'm going to be putting these together or thinking about separating them and taking out what's perfect and keeping the rest in jail. All right, let's begin our examples because we have a lot of examples again today. First slide is just asking you to multiply. Different than simplify, so just multiply. And so with the first example, we look, do they have the same index? Yes, they do. They're staying underneath the cube root, and 2 times 7 is 14. We should always try to simplify. So looking at our perfect cubes, can 8 go into 14 evenly? No, it can't. My second example, can we multiply these? Not in the form that they're in now. We'd have to write these with the same index, right? A square root has an index of 2. Talked about that in one of the class notes as well. Understanding square root has index of 2. Not the same number. We can't say the square root of 35 or the cube root of 35. That doesn't work. So we'd have to write these in exponential, get a common denominator, then we could write it under one root. But it just says to multiply, and we are going to say we can't. We can't multiply. Next one, we have the same index, so we can multiply them. So here's two separate roots. The rule said we can put all of this under the 5th root. 9 times 8 is 72. I'm going to do alphabetically. X to the first is x squared. Y to the second and y to the second will be y to the 4th, right? Working across, adding exponents. Now, underneath the 5th root, does 32 go into 72 evenly? No. And we only have 2 x's. We would need to have 5 or more for them to come out and for that to be considered perfect. We only have 4 y's, so same thing there. No y's, no x's can come out. Next set of notes say to simplify. Oh, we said, okay, so here it says a radical is simplified if the following are true. This is also part of the notes. I didn't write them down because I have them in front of me. You should have them written in already, or take time, pause the video, and write these in. The radicand has no factors raised to the power greater than or equal to the index. That's talking about using your perfects, figuring out if we can simplify like I was just talking about. Number 2, your radicand, which is the number underneath, no fractions. So what's under the root cannot be a fraction. You have to keep going if it is. And the third, we know, we've already done this in our trig chapters, that we can't have a radical in the denominator. So if we see that, we have to continue to simplify. We still have work to do. Once you say yes, yes, yes to all of these, that's when you know you're done simplifying. The rest of our notes is just to simplify. So lots of examples that we're going to go ahead and simplify. Cube root, looking at my cube roots, do I see 18? No. Do I see 125? Yes. So I want to break this up as the cube root of 18 over the cube root of 125 because 125 is a perfect cube. Is there a perfect that goes into 18? Does 8 go into 18 evenly? No. But the cube root of 125, it's perfect. It comes out of jail and it comes out as a 5. So we end up with the the root of 18 over 5, which is what we want because we don't want a root in the bottom. And the radicand can't be a fraction. 18 is not a fraction. And we checked to see if there was a perfect cube that went into 18. Variables run a little different. It's about are these numbers divisible by 3? And so like I'll ask myself, does 3 go into 12 evenly? If you say yes, then that is perfect. 2, there's not enough, right? There's not enough x's. We need 3 or more for an x to come out. So this is considered perfect because 3 goes into 12 evenly. I keep the negative on the outside. I'm going to break it up into the cube root of x squared over the cube root of r to the 12th. Not perfect, not enough x's. That's going to stay negative cube root of x squared. This is perfect. And how do we figure out how many r's come out? You just divide. 12, 3 goes into 12 4 times evenly. 12 divided by 3 is 4. So 4 r's come out, which will show r to the 4th. Done with that example. Fourth root of 243. Well, 243 is pretty big. So I'd start with 81 and I just check. You can do a factor tree. Most of you know how to do a factor tree to break that down. I'm just going to go ahead and allow you to use your calculators, but you should know how to do it without as well. Try dividing it by 81. You want to find the perfect that goes into it. So yes, it goes into it evenly. That's what you're looking for. If you see a decimal here, then your answer is no. So the biggest perfect fourth that goes into 243 is 81. How can I write that? I can write that as 81 times 3. So the fourth root of 81 times 3 still gives us this. And then this is where you can break it up into two separate, but I just like to say perfect or not perfect, perfect, not perfect. If you're saying perfect, it's coming out. 81's perfect, it comes out as 3. So 81's coming out. 3 is not a perfect fourth, so that's staying in the jail. Stays in the fourth root jail. A lot of students will lose that index, so don't lose that. What's going on here is multiplication, guys. So 3 times the fourth root of 3. I don't need to see the multiplication step, but I want you to understand that that's what's going on outside. So if anything comes out, it's being multiplied with it. All right, give me a second to flip to the rest of our examples, where we are going to continue to simplify. So the next one that we're going to simplify is a square root. Finding the biggest perfect that goes into 72. I'm going to throw an index of 2, right? And seeing that hopefully you agree that we can take out some y's. 2 doesn't go into 3 evenly, but we can break that up, right? We can break that up because it goes into it at least once. We're just going to have some left over, and then we're going to make that perfect. 72, biggest perfect that goes into 72. I always start with the number closest to 72. So like 64, I start with that. I know that doesn't work. 49, I know that doesn't work. 36 possibly. So I just tried dividing and it does work. So 36 is the biggest perfect, not 9. 36. 36 times 2. So under this root, I'm going to write 36 times 2. I like to write the perfect and then the not perfect. For the y, I'm going to do the same thing. How am I going to write that? Well, I want to have 2. That would be perfect, and then I have a total of 3, so I have to show the one that's not perfect. And then I just have x to the first. There's not enough x's to come out, so that's not perfect. So this is perfect and this is perfect. These 3 things are not. They're going to stay under. How do I know the y is perfect? Because 2 goes into 2 evenly. 36 under a square root is going to come out as 6. And the y squared is going to come out, again, just divide, simple division. 2 divided by 2 comes out as y. Again, when it comes out, remember it should come out as something different. It's coming out of the jail. So I've taken care of my perfects. What's underneath is 2xy. Those have to stay in the jail because they are not perfect. A fourth root, 32. 16 goes into 32, so I'm going to write 16 times 2 underneath this fourth root. So negative fourth root of 16 times 2. Perfect, not perfect. Okay, well, there's enough to come out, but 4 doesn't go into 5 evenly, so I'm going to break it up and write it as a to the 4th times a. And I hope you're seeing that this is perfect and this is not. Okay, so again, there's enough b's for something to come out, but 4 doesn't go into 7 evenly. So I'm going to break it up into b to the 4th, and then that's only 4 b's, and I need a total of 7, so b to the 3rd. 4, 5, 6, 7. This is perfect. Now I don't have enough b's to come out, so that's got to stay under. That's not perfect. Negative stays outside. What comes out? 16 comes out of the fourth root as 2. So 2 comes out. That comes out. A to the fourth comes out. 4 divided by 4 comes out as something different. It's going to come out as an A. And b to the fourth comes out as b, because 4 divided by 4 is 1. Those were my perfects, with that along with the negative outside, so I just multiply with that. Keep my fourth root. I don't lose my index. I have a 2 and a b cubed left in the jail. Done with that. Next problem is a cube root. Can we have negatives under the cube root? Yes, 27 is perfect, so that comes out as a -3. I'm just going to rewrite first, though, with the letter part. That's perfect. That's coming out. How do I write x to the 5th as perfect? X cubed, x squared. How do I write y to the 7th as perfect? Well, it goes into twice. I'm going to do y to the 6th and a y. That gives me 7 y's, and 3 goes into 6 evenly. And then z to the 6th, 3 goes into 6 evenly. This is perfect. None left over. No z's in jail. This will come out. It's perfect. Coming out, it's perfect. Comes out as -3. Coming out, it's perfect as x to the 1st. Staying in, not enough x's. Coming out, divide. Staying in and coming out. When it comes out as something different. And then what's under the cube root still? What's still in the jail? X squared. And, oops, that was perfect. And y to the 1st. These are staying. Not enough x's, not enough y's to come out. All right, next one. Still simplifying here. I'm going to look at this and ask to simplify. I have 8 under a 12th root. My power sheet doesn't even have 8. So at this point, I have to know, okay, how can I simplify this? And the answer is writing it in its other form. We know that a root can be represented with a rational exponent. So I'm going to write this as 2 to the 3/12. Index is the denominator, exponent is the numerator. 3/12 reduces to 1/4. And then I have the 4th root of 2. Now that is more simplified than what we started with. So like the multiplying one that we did either yesterday or earlier today we did it. I can't multiply these together because they don't have the same index, but how would I simplify? Because the directions are different. When it says to simplify, you actually have to do some work. So I have to write this as 7 to the 1/2 times 4 to the 1/3. And I know they don't have the same base, and that's okay, but what am I trying to do is I'm trying to write these with the same root. They'd have the same root if the bottom numbers were the same. That means I'm going to get a common denominator and have 3/6 and 4 to the 2/6. And now I can write these underneath the 6th root. And I get 7 cubed times 4 squared. 7 cubed is 343. So the 6th root of 343, I'm just going to double check that. Yep, times 4 squared, 4 times 4 is 16. And then we could just use the calculator. That's pretty big. Oops, if it was on. 343 times 16. And then I'd have the 6th root of 5,488. Final answer. Oops. Pause and then try this one just like that last one. Watch to see if you did it the same way. I would suggest pausing and trying on your own at this point. Press play when you're ready to check your work. This is going to be 5 to the 1/2 times 4 to the 1/3. Common denominator of 6. So I'm going to have 5 to the 3/6 times 4 to the 2/6. Now these both can go under the 6th root, and I get 5 cubed and 4 squared. 5 cubed is 125. 6th root of 125 times 16. 125 times 16 is 2,000. 6th root of 2,000. And you can go to your perfect 6 and try to find and see, but none of these are going to go into 2,000 evenly. So that becomes your final answer. A lot today. Have a great day, everyone. Let me know if you have questions. Bye.